All right, so that true-false question that we kind of took a stab at leads us right into what we want to do for separable differential equations. It has to do with the difference between solving these two problems. So what Aubrey was talking about, I want to show you. dy dx being equal to 2x versus dy dx being equal to 2y. Those two things are solved differently. When solving differential equations like this, when you have x's and y's as your variables, we use the moniker separate and integrate. In other words, to separate means anything that has something to do with x should be on one side of the equation. Anything that has something to do with y should be on the other. And so for the first question, we need to move the dx, multiply both sides so that we have dx on the other side. For the second equation, not only do we have to move the dx to the left, to the right, but we want to move the y over to the left. So separating the variables onto their respective sides. So for the first one, we end up with dy equals 2x dx. So we have nothing but a constant and some x's on the right-hand side. For the other one, we're going to have 2 dx, so we only have a constant in the dx. And where does the y go if we're moving it to the other side? You're dividing it, right? And so it's going to be dy over y. So this is the separate part of the process. Separate, and then follow it by integrate. So we just separated, and now we're going to integrate on both sides. And we'll show how you're going to get two different answers. So the first question, when we integrate dy, we get regular y. And when we integrate 2x dx, we get x squared plus c. On the other side, when we integrate dy over y, we get the natural log of the absolute value of y. And then that's equal to just 2x plus c. So you get very different answers. And so then the natural log side, we need to get y by itself. So we're going to apply an e to both sides. So we'll have the absolute value of y equals e to the 2x plus the constant c in parentheses. And then you won't be able to get y alone until you know what the domain of this is. Okay, we know that e to anything is always going to be a positive number. And since e to anything is always going to be positive, we can drop the absolute value, and we end up with. So we've got two very different answers based on two separate differential equations. And so that's the process called separate and integrate. Now those were two easy ones, so we're going to do a couple more challenging ones and see how that's going to go. So differential equations are solved with the idea of separate the variables and then integrate both sides. All right, so here's a couple questions. We're going to start with a doozy of a question, just because you're that smart. So you'll be asked to solve a differential equation that looks like this. dy dx equals, and it looks deceptively simplistic, e to the 2y minus x. And so we want to separate the variables so that we can integrate both sides. You're going to need to know some things about those properties of exponents before you're able to separate those. So remember, a subtraction of powers means e to the 2y over e to the x separately. Okay, a subtraction of powers means that. All right, now we want to separate the variables, and we want to put all the x terms on one side and all the y terms on the other. Does anybody feel comfortable trying that? Yeah, Tom? Okay. Okay? Okay, great. Before we integrate that, however, you're going to want to change it to e to the negative 2y times dy and e to the negative x times dx. That form is going to be easier for you to integrate. We would like our e's in the numerator so that we can integrate both sides. So we've done the separation, and now we're going to integrate the two sides. Okay, Trung, do you want to try the e to the negative 2y side? So the antiderivative of that. Okay, plus the constant, and I'm going to say C1 because it's the constant on one side. Okay, all right. Yi-Ting, you want to try the other one? Okay, so can I just do negative e to the negative x? Is that okay with you? All right, and then plus C2. Okay, so we can put, now we want to get y alone. So we separated, we integrated, and now we want to solve for y. So first of all, I'm going to combine my constants. So I'm going to have negative 1/2 e to the negative 2y equals negative e to the negative x, and then just plus an overall constant. So I'm going to do that first. And then I'm going to multiply everything by negative 2. That's so I am working towards getting y by itself. So I'll have e to the negative 2y. And I'm multiplying by negative 2, so I'll get 2 e to the negative x. And then when I multiply a constant by negative 2, it's still a constant. So I just multiplied all the terms by negative 2 so I could get rid of the negative 1/2 out in the front. Now I want to put things back into their fraction form. Well, I could take the natural log here. It's really, it's up to you. Do you want to take the natural log first or get it into a positive form first? Doesn't really matter. Natural log? Okay. So we're going to apply the natural log. So I'll have negative 2y equals the natural log of the quantity 2 e to the negative x plus c. There's a place algebraically that sometimes people will forget that the plus c has to be in the parentheses. They'll just leave plus c off on the end, but that's not the right way to tackle that, so make sure you've got that right. And so then y would be equal to the natural log of 2 e to the negative x plus the constant c all over the division of negative 2.
There's no way to reduce that anymore, that's it.
There are some additional things you could do. You could have the natural log of 2 over e to the x plus the constant over, you could do that, right? So that we don't have the negative exponent. That would be one thing. You could get a common denominator. Wow. Yeah, you could say, all right, it's 2 plus c e to the x over e to the x all over negative 2. So now it has a common denominator. Now that it has a common denominator, you could use the property of logs that allows you to subtract. So you could do ln of 2 plus c e to the x minus the ln of e to the x all over negative 2. And what's the ln of e to the x? So then you could say this is the natural log of 2 plus the constant times e to the x minus regular x all over. So I suppose you could if you wanted to.
I'll keep it.
Okay. Okay, good. Let's try another one. So the whole point, separate, integrate, get y alone. Separate, integrate, get y alone. And if you can, solve for plus c. What would you need, though, to be able to solve for plus c? You need an initial condition. All right. Now, I'm going to give you a little word to the y's. if you have an initial condition, solve for it right here. Because C is in a nice spot right there. Rather than doing all your other algebra and getting C buried in a bunch of parentheses, stop midstream and solve for C at a place where C is convenient. And then keep going with your algebra. It's going to be a lot easier mathematically for you to do that. Whoops. It just traced my finger. Okay, let's try one more. All right, so let's solve this differential equation. dy dx equals 2x parentheses 1 plus y squared close parentheses e to the x squared. Lots of fun with this one. Okay, boy, do the separation for me. Okay, I want to separate. I want all the y terms on one side, all the x terms on the other.
So, open the parentheses first.
Say that again?
Open the parentheses.
Open it? What do you mean?
Multiply those things.
I don't think I want to do that. That's gonna make it pretty messy. I just want to move it to the other side.
1 plus y squared
Mm-hmm.
parentheses over dy.
Other way around.
Yeah.
Okay, I want my dy in the numerator, and I want to divide by 1 plus y squared in the parentheses. Okay, that's what I want to do. And then what will I have left on the other side?
2x
Mm-hmm.
e to the x squared dx.
Okay. All right, now I have separated, and I'm ready to do the integration. All right, who wants to try the left side? What's the integral, Aubrey?
Inverse tangent y.
Inverse tangent y, very good. Okay, she recognized that as the inverse tangent of regular y plus the constant that comes on the first side. Okay, so some people look at that and they go, is it the natural log of 1 plus x squared? It's not. Okay, the natural log of 1 plus y squared, I mean. That doesn't work. The only way you'd have a natural log is if it was dy over y, or du over u, if you could make it a u substitution. All right, Trung, you want to try the other side? A u substitution, okay. What are you going to pick for your u? So then the differential, the du, is going to be 2x dx, right. So that's going to be a really nice, so I'm going to end up with e to the u du as my u substitution when I substitute and reduce out the 2x. So I'll have tan inverse of the quantity of y, plus the first constant, and now the antiderivative e to the u plus the second constant. And so then what I can do in my next step is combine constants and substitute back what the u stood for and just have an overall constant of c. So I've got the inverse tangent of y plus e to the x squared plus c. Okay, Yi-Ting, finish it out. Let's get y by itself. What do I do to both sides so I can have y equals? Yep, tangent parentheses. So I'm going to apply the tangent, and in the parentheses is going to go, right, and the plus c is in the parentheses. All right, so if you're solving for an initial condition, I would recommend to do that right here before you do the tangent on both sides, because c is in a much nicer place. It's not trapped and buried within parentheses. So if you've got an initial condition, solve for it there rather than solving it at the end like we typically have been used to. All right, separate and integrate. So a lot of, everything should work out nicely. You might need a u substitution or two, maybe on one side, maybe on both sides to have it work out. In fact, you could have done a substitution on this one Like maybe I would have said, okay, I'm going to have pick an a substitution or something and say a is 1 plus y squared. So then to see if that would work. And then you try it and you're like, I'm going to have 2y dy. And that doesn't work because I don't have my 2y. So this is not going to be, you might think it would work at the beginning, but it ends up not being a good u substitution choice because the 2y isn't present.